What I'll do today is start this new chapter on boundary value problems, and it's pretty much taken us 2/3 of the semester to build up to this point to be able to understand what the problem is. Um, so, what we did back in chapter 1, as you remember, was all the mathematical preliminaries about tensors and initial notation and how to deal with these types of quantities. In chapter 2, we defined or we described methods of how to describe mathematical ways of describing the deformation using deformation map, the F tensor field, C tensor field, strain tensor field, and so on. And we found changes in lengths, areas, and volumes. How do bodies deform? That was all kinematics. Chapter 3 was all statics, essentially, that sum of forces equal to 0 and sum of moments equal to 0. What does that mean for deformable bodies? We saw that we got equilibrium equations for at each and every point in a deformable body. Finally, we looked at material properties in chapter 4. And we said that we needed material properties to be able to get enough equations to be able to solve for all the unknowns. The unknowns that we are trying to solve for are the displacement field at each and every point of this deformable body. So if you go to any point, there's a ux, uy, uz, or u1, u2, u3, three components of displacements, which themselves are functions, really, three-dimensional functions of three variables, x1, x2, x3, right? So it's kind of a infinite dimensional problem. At each and every point, you're looking for three functions, which essentially are the displacement, or equivalently, you're looking for the deformation map, which itself is connecting the undeformed to the deformed configuration. So it's over a complicated domain like this, you could be looking for three-dimensional functions in general. It's a decently hard problem to solve, where those functions themselves must satisfy these governing differential equations as we laid them out, equilibrium equations for forces and moments, strain displacement relationships, that's SD, strain displacement relationships. If we assume that the material is linear elastic, where small strains or where the deformations are small, then we can use the Hooke's model, which gives me a relationship between stress and strain from this, so stress-strain relationship. And now we have 15 scalar equations and 15 scalar variables that we can solve for. Okay. At least we have equal number of equations and unknowns, so the problem essentially becomes well posed that there might be a solution. Whether we can find that solution or not is a different story. But we'll see what we can do for these types of problems. And I should also mention boundary conditions, of course. We know the two types of boundary conditions: Dirichlet, where displacements are specified; Neumann boundary conditions, where tractions are specified. So we've looked at this. And just like I said, in general, to be able to solve these problems means finding a displacement field at each and every point in the body, which is certainly not doable for complicated structures or for problems in general. For simple problems, you can find exact solutions. That would be an exact solution. If you can find a function that describes the displacement of each and every point of this body that satisfies all of these conditions, that would be an exact or an analytical solution, right? And that would be in the domain of solving these partial differential equations. These are partial differential equations because, as you know, div operator has all these partials in there. Definition of strain has gradient or all these partials in there. So this is a set of 15 different partial differential equations, and solving these types of partial differential equations in multiple dimensions on complicated domains is certainly not doable in general. People have in the past devoted a lot of effort to try to come up with exact or analytical solutions to common or simple problems. One example I've already mentioned maybe some time back was this example of a cantilever beam subject to an end moment. And we looked at the exact solution given by this form under the restriction that you assume that strains are small. And we saw that if you could generate the deformation map x from z plus u of z. That if you add this to the original locations, you get the map. From there, you can find out f and c and so on. But if you go and do that, actually, if you use the small deformation assumption, you can essentially check whether this solution satisfies the governing differential equations or not. So, for example, for this particular cantilever beam with a rectangular cross section of 2a and 2b wide and a length of L, let's say, if you take this solution and you plug it into this equation, given this displacement, you can find the strains. Given the strains, you can find the stresses, or the stress field really, over the entire body. And given the stress field, you can check whether equilibrium equations hold, these two equations hold or not. So since we have an exact solution to this problem, let's actually check whether it satisfies all these governing differential equations or not. And part of the calculation I've already done for you. Strain, as I said, is half of grad u, gradient of u, and we'll check that, plus gradient of u transpose. So let's check whether this is the gradient of u. Derivative of u with respect to x in here, that gives me nu over 2r, right? Or minus 2 nu over 2r, that gives me minus nu x over r. Derivative of u with respect to y, that gives me minus 2y over 2r, that's this one. A derivative of that with respect to z gives me minus z over 2r, and so on. So if you can check that this is gradient of u, this is gradient of u transpose, and if I add these two, you should be able to see that this off diagonal components cancel off, this off diagonal component cancels off. Let me do the same direction at least. And similarly, gamma y here, this cancels off, and z over r cancels here. So what I'm left with is minus nu x over r, minus nu x over r, and x over r. Everything else in the strain tensor is 0. This clearly gives me a strain field over the entire body. Okay? No matter where you are in the beam, it gives me a strain field as a function of x, which makes sense because it's a cantilever beam under constant moment. So at each point, the moment is the same, which means that the strain would just be varying linearly through the cross section, right? Through the depth of the cross section. At every point, it would be the exact same moment. So the strain field is clearly not a function of y and z. It's only a function of x, where if you go in this direction above or below the neutral axis, you get positive strains, tension. You go above the neutral axis in this direction, that's compression, negative strains. So that kind of strain field makes sense. And if you calculate the stress field from this, so I've done that as well here, using that Young's modulus and Poisson's ratio as your question.
R means what?
R is actually the radius of curvature, where if you have a beam in pure moment, then it makes actually an arc of a circle. So that's what that R denotes. Okay. All right, so so if you plug in the material property, that is the Hooke's model, then we can see that trace of R is nothing but 1 minus 2 nu times x over r, identity tensor. That's the trace of epsilon times the identity tensor plus 2 over or c over 1 plus nu of epsilon. So if we do that, let's see what we can simplify this to. X over r times identity and c over nu. So what I'll do is I'll pull out c over 1 plus nu outside. So that takes care of this factor c over 1 plus nu times nu x over r times identity. That cancels off with these two terms. And what I'm left here with is 0, 0, and 1 plus nu x over r. I can then further cancel this 1 over nu with this factor outside, so I cancel that off, and what I'm left with is c x over r. So every component of the stress tensor field is 0 except the S33 component. Does that make sense? If I have a cantilever beam under pure moment, the only non-zero component of stress you would have would be on the cross section only in the 3-3 direction. Make sense? So with that, we can say that S33 would be C times X over R. C times X over R. And hopefully that should look familiar to you. If you remember this set of equations from your beam mechanics, sigma is equal to E y over R. In that equation, we used to have y-axis above and below the neutral axis. In this case, we have the x-axis above and below the neutral axis. So you should be able to see that this equation is just a change of variables of your familiar equation for mechanics of beams. Okay, so now that we have the strain field, the stress field, we have already just made sure that this equation is satisfied because we actually used the expression to calculate strains. This equation is satisfied because we used this to calculate stresses. Is stress tensor symmetric? Is the stress tensor field symmetric? Yeah. And how about the first equation? Divergence of S plus B equal to 0. Is that satisfied? How can we check whether this satisfies the divergence of S plus B equal to 0? Check. What?
B is 0.
Okay, yes. So actually it would be, let's actually assume that B to be equal to 0. Let's say B is, there is no body force. If there is self weight, then the beam will deflect under gravity, which would violate the assumptions behind this true solution. Let's assume that the self weight is negligible. What would be the divergence of this tensor field? Obviously, the first two zeros. How do we find divergence, by the way? Let me step back. So if I have a tensor field, I can take that tensor field, apply it on the grad operator, right? S acting on grad is divergence, and grad operator would be partial x, partial y, partial z. Clearly, the first two rows give me 0. The third row, it says take the partial of this term with respect to z, not with respect to x. That would be 0 as well. So clearly, that divergence of S is also 0, which means that the equilibrium equation is also checked. And you can verify, I won't do the boundary conditions, but you can check that if you take the stress field, act it upon the normal on this face, act it on the normal on this face, you will get tractions that satisfy this moment, that result into this bending moment. Go ahead. Yeah. So this is an assumption behind this exact solution. As I said, in general, even for the simple problems, if you have body force, the problem becomes pretty much almost intractable. This exact solution assumes that body force is 0. Right, it's an assumption, which obviously gives you an idea of how constrained these exact solutions are. These exact solutions, if they don't, we can't neglect body forces in general. We can't neglect the weight of our structure for most problems, right? So if we make those kinds of assumptions, that tells you how restrictive these exact solutions are. But at least it gives you a sense of what an exact solution might look like. It would be a function of 3 variables over the domain of a body. Okay. So I'll let you check the boundary conditions, but you can take it on my word that that this is an exact solution to this particular problem if you neglect the body forces. Okay, let's take another example. Here's a circular bar with a circular cross section, and I'm applying a torsional moment to it. Okay? This is another relatively simple problem. And the exact solution to this problem, actually, it's an example in your book, and it's also another one in a very well-known structural mechanics book. The displacement field is given by this expression, minus beta z2 z3 and plus beta z1 z3. So as you, and I think maybe you've even looked at this map before. If you think of this as, if you take this as the displacement field, what would be the strain field? Maybe take 30 seconds and see if you can write down the strain field from this displacement field. So all you need to do is to take the gradient of this displacement. This displacement is two components in E1 and E2, one in E1, one in E2. All right, let's do those calculations together. This is a vector field, right? Displacement is a vector field. How do I, if I take the gradient of a vector field, I should get a tensor field, which is why, of course, strain is a tensor. So how do I take the gradient of a vector field? You remember it's V dyad grad, right? So if I list out the components of the vector field in a 3x1 vector, I take the dyadic or the outer product of that with the gradient or the grad operator, which means basically that I need to take derivatives of this E1 component with respect to Z1, Z2, Z3. Derivative of this with respect to Z1, 0. Derivative of this respect to Z2 minus beta Z3 and minus beta Z2 with respect to Z3. Similarly, the second component would be derivative with respect to Z1 would be beta Z1, sorry, it's beta Z3. Derivative with respect to Z2 is 0. Derivative with respect to Z3 would be beta Z1. And essentially, if you, and the third one is all zeros, but that is gradient of u, so I'll write that actually here. That part is gradient of u. If I add now half of gradient of u plus gradient of u transpose, if I want to calculate that, then once again, what we'll do here is these two terms cancel off, right? If I transpose this, then these two terms cancel off. And if I add the transpose of this here, then that would give me, I'm sort of overwriting it here, but let me then make some more room. Maybe I'll write, so actually I'll write epsilon here and note that this is gradient of u and epsilon is gradient of u plus gradient of u transpose and factor of half. So that would be represented by half times beta. I'll pull beta outside, and I have 0, 0, 0, 0, and minus z2, z1, uh, minus z2 and z1, and 0. So if I take the transpose of this matrix and add it to itself and then multiply by the factor of half, this is what I get. Clearly, this strain field does not have any normal strains. It has two components of shear strain in the 1-2 plane, which makes sense. That's what the torsional moment would do. Now, if I take that strain field, use my Hooke's model to come up with the components of the stress. By the way, this should not be equal to; it should be represented by, and it would be represented by this trace of epsilon is clearly 0, so this entire term drops out, right? 2 mu and then half beta just becomes mu beta. So what's going on here? So mu times beta, and then epsilon as it is would be 0, 0 minus z2, z1, 0 minus z2, z1, 0, 0. That's my stress field. Clearly, it varies from point to point, as it should. What about checking whether this satisfies the governing differential equation? Well, again, we would have to calculate the divergence of this stress field. Okay, which means taking the stress field, acting it upon the divergence operator partial z1, partial z2, partial z3. This first row derivative, when I act it on this, I get 0. And second row, of course, acting on that, there is this derivative with respect to z3 is 0. This derivative with respect to z1 is 0. This derivative with respect to z2 is 0. So clearly, divergence of S is 0 vector. Again, we'll assume body forces are 0. And therefore, we verified that the equilibrium equations are satisfied. And once again, I'll leave it for you to check that the boundary conditions are also satisfied. That if you take this stress field, act it on the normal, you will get a traction profile. Okay. If you integrate those tractions on this surface and on the back surface, then you'll be able to equate it to a torsional moment. Okay. So this once again this solution again checks that all the equilibrium equations, the strain displacement relationships, the stress strain relationships, they are all satisfied and the boundary conditions are satisfied. So this is yet another example of an exact solution. This is what, but keep in mind again, we neglected the body force, and this body itself is a simple circular bar under a uniform torsional moment. So it's not a very complicated problem, and only then are we able to generate these types of exact solutions. In general, as I said, these exact solutions are not easy to come by. For anything complicated, reasonably complicated geometry, there's usually not an exact solution that you can find. So what do you do? If you can't find an exact solution to a problem, what do you do? Yeah, you make more assumptions and you try to find other approximate solutions, right? That's why we study all the structural mechanics that makes lots of these types of assumptions. And but the critical thing again is to make sure that you understand those assumptions, what are the limitations of those assumptions, and and how does that affect the solution that you are getting? Go ahead, Vivek.
It's totally related, but are these the assumptions in the simulations the guy was talking about?
Okay, I was hoping somebody would bring that up. So, yes, we had a good seminar yesterday where computer simulations seem to have gotten a bad rap there, right? But keep in mind, I think I agree with most of what he said, that 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 we are proposing a new methodology for design without actually checking it against ground truth. But keep in mind, computer simulation is a tool. Okay, it's just like a strain gauge, for example. Strain gauge is a tool to study the behavior of stress or strain or something at a point. If you don't install a strain gauge correctly, will those readings make sense to you? So, in the same way, computer simulation is no more complicated than a calculator that you have in your hand, right? If you don't use the calculator correctly, who is to blame? Is the calculator to blame, or is the engineer to blame, right? So I think the point remains that indeed we have to understand what are the assumptions that go behind these computer simulations. The answer is not that we should not use computer simulations. The answer is that you all should try to inform yourselves better of what are the assumptions that go behind these computer simulations, which is why we are studying all this deep mathematics and deep mechanics to understand exactly how this is used to build up computer models that give you some results. If you look at the results coming out of computer model, they all look very colorful and nice, and you're tempted to believe it, right? But judging, yes, you can maybe reason that, okay, yeah, this kind of looks reasonable. If I apply a load this way, then it might behave stresses like this way, and so on. But that's not a good way to understand the results of your computer simulation. You always to be skeptical of those results. But what is better for you to do is to understand what are the assumptions that went behind. Why did you get this computer output? Why did you get this result out of the computer simulation? Whether some of the assumptions that you made are justified or not, those would be the right questions to ask in that case. But other than that, yes, absolutely. There are lots of assumptions that go into any model. Okay, all of these things are just models. All right, so I think that kind of brings me to common assumptions that people have used in the past to generate still more other exact solutions. Since the three-dimensional problem in general is so complicated that I can't generate exact solutions for slightly complicated geometries or slightly complicated loadings, let's make some assumptions to simplify the problem, and let's see if that helps us generate some other exact solutions. For example, people somehow are able, for some certain problems, are able to make the axisymmetric assumption, which means that, for example, like in a nuclear cooling tower, that's a axisymmetric structure, right? There are lots of structures that are axisymmetric. You can make those types of assumptions, and for that class of problems, you get a slightly different set of partial differential equations and a whole line of solutions. For plane stress and plane strain, we have talked about that, right? Plane stress is problems with where the third dimension of stress, the third component of stress, is always zero. That happens for thin structures generally. Or plane strain, where the third dimension of strain is zero. The third component of strain is zero, which happens for long structures, if you look at a cross section. Even so, you can make those types of assumptions to come up with simpler exact solutions. And beam theory or shell theory, plate theory, these are all theories of actually structural mechanics. So what we have been doing till now is more of solid or continuum mechanics. We said there is a body. We didn't say that it's solid or fluid or what. We just said what we dealt with were deformations and describing deformations and equilibrium conditions. They hold for any material, right? that was more of a solid mechanics description. If you go with one of the structural mechanics theories, you would end up with beam theory or plate theory where there are assumptions. What's the assumption for beam theory? Plane sections remain plane, or rigid sections remain rigid before and after deformation. A huge assumption. But it works very well for long, slender structural components. If our structures are made out of beams and columns only, works perfectly fine. And for those types of problems, you are able to get some exact solutions. For plate theory, similarly, you are able to make assumptions behind behavior to get some exact solutions. And those fall in the realm of structural mechanics, as I said. What we will be focusing on is not necessarily making these types of assumptions to simplify the complicated 3D problem down to 2D problem or a 1D problem and then find an exact solution. We are not interested in that, because that approach works for certain types of structures, certain types of bodies. In general, that approach does not work for all for more complicated structures that people are starting to build today. And as you pointed out, commonly these days people are adopting computer simulations or computer models to be able to study the behavior of a building that has been designed or that has been constructed. Now, these computer models rely upon approximate numerical methods. Okay, so approximate numerical methods, of course, we make certain assumptions behind that. But I'll also say at that point that if you build a model for, let's say, as complicated a three-dimensional structure as you want, let's go back to this guy. You've seen like maybe a picture of this maybe long back when we introduced that, like this, right? This indeed is a computer model of that structure, and if you make the model properly, and if you choose the right parameters, it is possible to get the best possible solution to this exact problem. One way to do that is you see these divisions in this body, right? These are, for some of you might know, finite elements. If you keep using smaller and smaller finite elements, lots and lots of divisions, you will actually approach the exact solution to this problem in the limit of mesh refinement, where the element size goes to 0. So if it's a well-posed problem, if it's a solid material, this computer simulation has the potential to give you almost an exact solution to it. Okay, but in real life, of course, materials are not uniform. Material behavior. If it's a concrete, it's very hard to write like a material model for it, a stress-strain relationship for it. Certainly, it's not linear elastic. So there are additional complications to that. But at least the way that we have framed the problem, at least in the way that we have framed this problem, using computer simulation, you can get as extremely close to that exact solution, as close as you want. So our objective in this course, in the remainder of this course, will be to understand how to set up these types of approximate numerical solutions. If you're interested in exact solutions, pick up that book by Timoshenko and Goodyear. Take a look at, I don't know how many different types of assumptions for different types of problems in here. There are lots and lots of examples under certain types of assumptions. They've given you methods which essentially overlap with the mathematics of partial differential equations. Really, what your exact solution means that you have to solve those PDEs. So rather than getting into that, we'll try to generate approximate numerical solutions. Before I do that, a quick note about plane stress and plane strain that I didn't mention last time when we did those examples. You see these reduced set of equations here. These reduced set of equations allow you to relate the stress and strain for only those two x, y dimensions. For plane strain, you get this relation. Plane stress, you get this relationship. Keep in mind that epsilon ZZ, the through thickness strains, are non-zero in this case. For plane stress, you get slightly different equations, still 3 cross 3, but the 3 or the ZZ stresses are non-zero in general. And the way we get this is actually from materials. You remember we set up this big, huge 9 cross 9 system. We boiled it down to this 6 cross 6 system. Now, if I say it's a plane strain problem, for example, plane strain means epsilon 33 is 0, epsilon 23, epsilon 31 is 0. The only non-zero components are epsilon 11, epsilon 22, epsilon 12. So that immediately gets rid of a lot of these constants and leads us to a simpler 3 cross 3 relationship. That's what I've written out here. Okay, so it's not terribly difficult to derive this, but it comes in handy when you are solving plane stress or plane strain problems. Okay. All right. So as I was saying, we are going to be trying to understand how to generate approximate numerical solutions and trying to understand how good are these approximate numerical solutions. Now, for general three-dimensional problems, that's a little bit of a complicated problem. Okay, that's a little bit of a complicated process, but it's a process that will be mimicked very closely by what I'm calling as a one-dimensional boundary value problem. Maybe I didn't state this, but this entire thing is called a boundary value problem. These governing differential equations, boundary conditions, the definition of the domain, this is in the partial differential equation language, this is called a boundary value problem. What we are going to do is to study a simpler one-dimensional boundary value problem by actually studying a three-dimensional problem where the behavior is just in the one-dimensional. So we are going to look at this three-dimensional bar with a circular cross section, some traction applied on the end face here, some body forces acting on it through body forces are distributed forces per unit volume. If you want to think of it, think of like a flexible rubber bar hanging from the ceiling, right? That's if you think of that as a ceiling and hanging down with an end load applied at it, the body forces represent the self weight, and TL, the traction at length L, is the external force applied to this. So this is a three-dimensional problem where I hope you can see that the behavior will be all along x, all along this x dimension. Okay, it's very similar to one of the experiments that we talked about. Anybody remember what experiment I'm talking about to determine material properties? Uniaxial. The behavior is uniaxial in here. The state of stress is not uniform along the bar, okay, but at any point the behavior is uniaxial. If you go to any particular cross section, we are assuming that the behavior is uniaxial. So that means that in general, if I take this as E1, E2, and this as E3, which later on we'll substitute x for that dimension, can I say U1 and U2 are 0? For this problem, if I have like a rubber bar under self-weight, traction applied, it will extend. And what about the lateral dimensions? Would it be 0? No, in general they won't be 0. It depends upon the Poisson's ratio, right? So those would be non-zero, but how can we find them? If I Right. So if I know the strains, so let me, so indeed, those two would be non-zero, unknowns, but they will be dependent on U3. This thing I will call it's a scalar function of x. Okay, that's the main unknown that we are going to try to find for for this particular problem. What about the strains? Would there be any off-diagonal components for this strain? Any shear strains in this bar? No. In the uniaxial state of uniaxial test, we did not get off-diagonal strains. So indeed, all of those would be 0. And as I said, the main strain that we are looking for is this E33. If we have E33, then E11 would be equal to E22 would be equal to minus nu E33. You agree? That's the definition of the Poisson's ratio. Poisson's ratio times the longitudinal strain will give me the strain in the lateral directions. Once I have that, I can easily calculate U1 and U2. Okay. So this E33 is equal to partial U3 partial Z3. I've already replaced U3 with U and Z3 with X. So this is equal to, I'll write total strain now, du dx, because I'm not worried about the other dimensions. This I'm just writing it as a single variable problem. The only independent variable in my problem ultimately would be x, and the displacement in the x direction as a function of the position of the point in this direction x. So this is the strain. This is the definition of strain, which I will call U prime. So now I'm starting to use some notation, additional notation here. Strain along the length of the bar is given by du dx, which I'm just representing as prime, U prime. Okay. All right. How about stress? I will use the Hooke's model, and you can see in terms of Young's modulus and Poisson's ratio, if I plug that in, trace of epsilon would be what? Trace of epsilon would be E33. This would be minus nu E33. This would also be minus nu E33. So we get 1 minus 2 nu E33. This 1 minus 2 nu, this 1 minus 2 nu cancels off. I get a factor of C over 1 plus nu, C over 1 plus nu here, and nu times E33 plus epsilon 33. If you simplify that out, you should get that the only non-zero component of stress would be S33, which would be equal to Young's modulus times E33, which is the exact same expression that we got for the uniaxial test, right? In the uniaxial test case, the only non-zero component of stress was S33, and but the strain was not all not just this was non-zero. These two are also non-zero because of lateral contraction. So this is the same relationship that we had for the uniaxial test, and all I'm doing is replacing it with C times U prime. This was the strain times Young's modulus, gives me the uniaxial stress. I'm also going to denote this stress sometimes with sigma. S33 I'm going to call sigma. Okay. So this leads me to the equations that divergence of S, if I have a 3 cross 3 stress tensor, divergence of that would be, maybe I'll take a side here. If I have 3 cross 3 stress tensor where everything is 0, and divergence of that would be partial Z1, partial Z2, partial Z3. But keep in mind, I've replaced Z3 with X. Okay. So divergence of stress would be equal to what? Zero, 0. There's nothing up here in the matrix. Only the last row, d sigma dx. That would be what we would get here, d sigma dx. Agreed? So I'll take this term, only the third element of that equation is what I'm going to look at, and I'm going to write that in here. That would be d sigma dx plus body force in the third direction. Let's assume that there are no lateral body forces, but body force can be uh, only along the longitudinal direction. So d sigma dx plus body force is equal to 0. And that gives me one of the equations. And just to be sort of consistent with the book, maybe I'll also write it like this: sigma prime plus b equal to 0. This equation must hold for all points x in between 0 to L. For all cross sections in between 0 to L, this equation must hold. Right? That's just a restatement of the equilibrium equation, which said that this equation must hold at all points in my body. I'm saying this equation must hold at all cross sections in my body. What about strain? Strain we have already defined out here, that strain is equal to u bar at all points x in my body. Material properties, it's the one-dimensional equivalent. That material properties are saying that sigma is equal to Young's modulus times strain for all points in my body. And finally, I have boundary conditions. There are two boundary conditions. One of the ends, for at least in this particular example, end where x is 0 is fixed, and where x is equal to L has some applied traction. And so this would be Dirichlet boundary condition where displacements are specified, and this would be Neumann boundary condition where tractions are specified. Okay, which we would write as, on the Neumann boundary, tractions are given by the Cauchy stress traction relationship. Correct? Stress tensor has every component 0 except the 3 non-zero equal to sigma. What is n? What is the normal n on this face? E3. Which means that S acting on n would be what? So this S with sigma in the T3 component, E3, just as you said, is 0, 0, 1, which gives me the traction which would be equal to 0, 0 sigma. And to be explicit, that actually it is sigma acting on plus 1 is what we are talking about. So sigma acting on plus 1, that's on the right face. Sigma acting on minus 1 would be on the left face, right? So that's the way I'll write my boundary condition on the right face. So that gives me traction T at TL, T sub L. Traction T sub L is equal to sigma acting on plus 1. That's just the one-dimensional equivalent of the Cauchy stress traction relationship. Okay. On the left face, U at 0 is equal to some specified displacement. This could be non-zero or it could be 0 itself. So what this is saying is that the displacement at x equal to 0 is given to me. It may be non-zero, but it's given to me. Okay. So that's a restatement of my governing equations from a complicated three-dimensional body down to something very simple, one dimension. These are equations we can very easily integrate and solve. Okay, and there's an alternate derivation of the same set of equations given here, but I'll not go through that. I'll very quickly also state that if you plug in these two, stress and strain, back into this equation, you can actually simplify that down to Cu prime, that's stress, plus prime plus b equal to 0, and then the two boundary conditions, sigma L is equal to TL is equal to sigma acting on plus L, and U at 0 is equal to U0. So this is for all points x between 0 and L, and this is at x equal to L, this is at x equal to 0. So this is also at x equal to L and at x equal to 0. So these are the set of these three. Essentially, this equation is what we'll be trying to solve to understand how this type of problem behaves. The good thing about this equation is that we can generate exact solutions to this equation. And we'll also generate approximate solutions to this equation and compare them. We cannot do that for three-dimensional problems, but for this particular problem, we can do that, and we can understand what is the consequence of our assumptions. Okay. All right, so I'll stop here, and then we'll come back and do that on Friday.